All right, in the meantime, I installed a theme to use here. So what else is happening here? Yeah, this line of code here. So this line of code is counting the number of missing values in the total bedrooms column of the testset data frame. This is a test set. These are the total bedrooms. It's null, and we check the sum of it. Why would we use this? We just use this to detect missing data before training a machine learning model, and it helps us decide whether to fill missing values or to remove rows, which are some of the practices when we encounter situations like this. All right, to find the probability that a random sample of 1,000 people contains less than 48.5 female or more than 53.5 females, when the population's female ratio is 51.1, we use binomial distribution. So what's a binomial distribution? It's a type of probability distribution that describes the number of successes in a fixed number of independent trials. And each trial has only two possible outcomes, either a success or a failure. So it's fixed in size. So we have the binomial distribution. So it has fixed number of trials, only two outcomes per trial, same probability in each trial. Reality in each trial, and the trials themselves are independent. So let me just go on a new line. So if we flip a coin 10 times, and if the success is getting heads and failure is getting tails, and the probability of either one of them is 0.5 if a coin is fair, and we have 10 total trials, we need to answer the question, what is the probability of getting exactly 6 heads out of 10 flips? And the formula for binomial probability is P K. So this is the probability of getting exactly K successes. This is N is the number of trials, K is the number of successes, P is the probability of success. This is the binomial coefficient, and we can actually write this as follows. So we are looking to see what is the probability of getting 6 of these guys. So in total we have 10. We want 6. Probability of 6 probability is 0.5 by 6. 1 minus p, 1 minus probability 0.5 multiplied by n minus k, it's 4. So this is around 0.204, or so for the uninitiated, we have the binomial coefficient, which basically means 10 chooses 6 to represent the number of ways to choose 6 sets out of the 10 flips. And this is actually the same as if this is n over k. So this is n factorial, k factorial, n minus k factorial. So this is going to be using the value that we have here, 10, 6 factorial, 4 factorial, and it's going to be 10 times 9. It's 2 times 1. What are you going to have here? 6 times 5 times 4 times 3 times 2. Do you see something? We can basically get rid of this and get rid of this. 2 times 1. So this is going to be 24. Above we will have 10 times, say times, so it's going to be 5040 over 24 is 210. So what basically this says, it says there are 210 different ways to get 6 heads in 10 flips. We are basically just asking ourselves, how many ways can we choose 6 heads from 10 flips, and then we multiply this by the probabilities of heads and tails to get the final probability. All right, let's continue. What we have here shows how to compute the 10% probe of getting a bad sample. Okay, I can skip this, hopefully. Oh, this is what we need. This is what we need. This person right here. I love this theme. The only thing I don't like are the red outlines when I'm selecting code, because it feels like I have an error state, which is not true basically. So here we are creating an income category column. Here in the housing dataset. And what we do, we group together. We are actually bidding the median income values into 5 different categories. So the PD cut is used to split continuous numerical values into bins, into categories basically. So we need to do this. I'm just remembering the logic of it. I don't need to remember anything more complex. I'm just remembering the logic of it. So the PD cut is used to split continuous values into discrete categories. And we are bidding median income into the bin edges. Sorry, these are the bin edges. Or income ranges, and each income range is assigned to a category based on these bins. So we have from 0 to 1.5, which is 1, which I assume means very low income. From 1.5 to 3, it's low income. From 3 to 4.5, it's 3. From 6 and above into infinity, it's 5. So basically this includes all values greater than 6, and these are the labels of it. Simplifies our data because it's easier to work with categories instead of raw numbers. It's good because we also need to stratify our sampling, and this reduces the impact of outliers. And now, if I have it here, now we have a nice visual representation of all of this. So what am I doing? I'm counting the values, I'm sorting it, I'm plotting the indices. Okay, I set the labels and I'm showing the plot. That's it. Pretty nice. And now we need to do stratified sampling based on the income category. Nice. So now we can do stratified sampling based on our income category. So this code that we have here actually performs stratified sampling, and it's doing this in order to split the housing dataset into training and test set multiple times. 10 different splits, and it ensures that each income category is proportionally represented in both sets. So yeah, this is the stratified shuffle split. Here, okay, first of all, we imported it from scikit-learn. It's a technique used to split data while preserving category proportions. So here we have the number of splits, which creates 10 different train test splits. Again, 20% of the data is assigned to the test set. We have the random state. And here we perform splits. So we have the train index and test index. And in this data set, so it splits this data set into train index and test index 10 times. And it uses the income category to ensure the train test split maintains income category proportions. All right. Here we are extracting train and test sets using iloc based on generated indices. Same thing here. So if I print here, print train index, what am I having? Out of think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So these are our indices. So now we have 10 different stratified splits. If I print out this, it should have 10 different stratified splits, right? This is a list, it's not a... all right. So what's the size of this? It's rows divided by 11 columns. All right. And each pair should preserve the proportion of income category in both train and test sets. Alrighty, for now we can just use the first split. And I think we have it somewhere. This is the code. I'm gonna remove the print statement as I don't need it anymore. I'm gonna run this. I'm gonna run this. So this is the first split. Right. So stratified sampling is fairly common. There's a shorter way to get a single split using the train test split function with the stratify argument, which is this line of code here. So this line of code, I don't know if you can see it, just splits the housing dataset into training and test set using stratified sampling to ensure that each income category is proportionally represented in both sets. Same thing as above. So train test split is splitting a dataset into training and test sets, and it randomly selects rows for each set while preserving the original distribution of a categorical feature. Yeah, we have housing, which is a data set. We have test size, which is the test size. 20% of the data goes into the test set. The rest, 80%, remains in the training set. We stratify our set on the income category feature in housing, and without stratification, some income categories might be underrepresented in some tests. And this is the random state 42. And this line of code actually points and displays the income category proportions in the test set. So what do we have? We have the following distribution, 35%. So it's what, 35% of data points, rows are found in the third bucket, 31% in the second, 17% in the fourth, 11% in the first one, and 3%, 11% in the fifth one, and 3% in the first one. So these introductory episodes were mostly spent on test set generation, which is a neglected but often critical part of machine learning projects. Now, let's explore the data in order to gain insights. Okay, so this is actually quite interesting and important as well. So we split here so this table compares the distribution of income categories in the full data set. I think we have housing here somewhere. Do we? Here. So we compare the distribution of income categories in housing in the stratified test set, which is this guy. I think we calculated it, yeah, above. And in the regular test set, which is a randomly split test set. We calculate the errors, basically. So, okay, here we have some regular split and a randomly generated test set. The stratified one is above, and housing is here as well. So we compare them on. Okay, this is the title of the income category. I don't need this. I need, yeah, I want to explain what happens here. So the function income cat proportions calculates the proportion of each income category in a dataset. And how does it do it? So we count the occurrence of each category, and then we divide by the total number of rows to get percentages. So if, I don't know, data income, actually, if we provide housing here, and if housing income category has, I don't know, something like this, let me maybe write this. In the fourth, we can have 15 rows, and in the fifth, we can have 10 rows. So in total, I think it's 100 rows. So next, what we want is to calculate the percentage distribution of income categories. So this method that I just showed you, income cat properties, would calculate it for each of the buckets specifically. So in the first one, I have 30 divided by 100, 0.3, 20 divided by 100, 0.2, 25 divided by 100 is 0.25, this one is 0.15, this one is 0.10. And this basically just gives the percentage distribution of income categories. And that's it. Basically, we are comparing the overall difference. So if I'm not mistaken, the overall distribution is, yeah, on regular housing. So we have, this is these are the proportions on each bucket. Next, we have the certified test set, which actually is quite close to the one that we have. It's only 0.02 here 0.01, so it's quite close. But the randomized one doesn't exactly fit the buckets here. So here we actually create an error percentage for both stratified and random test sets. And if you can see, the stratified test sets are all under 1%, but the randomized are, well, with larger errors, we mean that the test set is not representative enough. But if the error is close to 0, the distribution is well preserved. And then we just converted it to percentages, I think here. Yeah, that's it. Now, let's talk about visualization of data. So, all right. So what we did here is is a copy that we created of the training set in order to work and visualize the training set directly. Of course, experiment, create some transformations and visualizations. So we created a copy in order to do everything on the housing variable that we created. If the training set is by chance, I don't know, very large, there's a possibility to create a sample, maybe an exploration set, to make manipulations easy and fast during the exploration phase. Okay, so this code is creating a scatter plot of the housing dataset, which is based on longitude and latitude, and it visualizes geographic distribution. So what this method does is it creates a scatter plot of the housing data frame. So we have the longitude on the x-axis, we have the latitude on the y-axis. Let me just show this. And here, yes. And we have the grid, which is displayed for better visibility. And basically what we do with this is just help visualize house locations on a map. And in some sense, this resembles the California map, right? And then we just show it. All right. We have another plot here. So again, it's a scatter plot with longitude and latitude. And we also have the alpha property, which does which handles the transparency or opacity of elements in a plot, and it accepts values between 0.0 and 1.0, and an alpha value of 1.0 means that it's fully opaque, which is default. 0.5 is 50% transparent, and 0.0 is completely transparent. With 0.2, we make points more transparent, so densely populated areas become more visible. So before I move on, let me just see, just to add, because if we set the alpha path option to 0.2, we can better visualize the places where we have a higher density of data points along these lines here. Alright, we have another scatter plot here, and what this one does is the following. So this code creates another scatter plot, and another one that is going to help us visualize housing locations. So here actually the size of each dot represents the population, and the color of each dot represents the median house value. And we have a color bar here that is added in order to show value ranges. So let's just break the code quickly. So we already know this creates a scatter plot. We have the longitude and latitude. We are creating a grid for better visibility and readability. So the point size is the size of each point, which represents the population in that area. Larger dots mean higher population, like this one here, or a couple of these points here. But we divide it by 100 to ensure that the points are not too large. If I do this, not very pretty. So that's why we have the 100. What else we have? We have labeled this population. Next thing, we have C, which is the median house value, which is the color of each dot, and is based on median house prices. Expensive areas are in red, the cheaper ones are in blue. And why we use this color scheme is because we use the color map JET, which uses the JET's color scheme, which paints low values with blue, medium values with green and yellow, and the high values with red. Of course, you also have the color bar, which adds a color legend showing the house price scale. And what's this? We have the legend, which labels the point size as population. Share x-axis is independent, and this is the figure size, 10 by 7 inches. The argument share x false pixels on display, but without it, the x-axis values and label are not displayed. Okay. Alrighty. This is good actually. With this, we did a visual geographical analysis. So we saw housing trends across region, and we combined multiple data points. And it's really useful for, I don't know, real estate insights and pricing models. So I assume this is the same. Yeah, it is the same thing. Basically, it's a beautified version of the previous figure with an image of California added in the background, nicer labels, nicer label names, and no grid. All right, so we actually can see some sort of value from the visualization. We can see that the most expensive places are next to the ocean, and the housing prices are also related to the population density, because the most expensive locations are closer to where most people live. All right, let's look for correlations. All right, the data set. The numerical argument defaults to false. All right. All right, here, this line of code is, okay, this line of code uses the core method, which calculates the percent correlation coefficient for every pair of numerical columns in the dataset. Because the dataset is not too large, we can actually compute correlations between different attributes using the correlation matrix. Why do we do this? In order to identify relationships between variables and understand how strongly they are related. So the person's correlation coefficient is an algorithm that measures how strongly two variables are related. It ranges from -1 to 1, with 1 being a perfect positive correlation, 0 being no correlation at all, and -1.0 being perfect negative correlation. Alright, let's print this out. So now we can look at how much each attribute correlates with the median house value. So with this line of code, we retrieve and sort the correlation values of all attributes in the housing dataset with respect to the median house value, which is the house price. If we go up here, all the way, median house value, yeah, which is just the house price. Where is it? Here. So it helps identify which factors are most strongly related to housing prices. So this is our correlation matrix. This is our median house value. We sort the values in descending order, like this. And here we have, okay, the median house value has a strong correlation to itself, but median income is a strong positive correlation. This is somewhat a weak positive correlation. These are all very weak. Population has almost no correlation, and longitude and latitude have weak negative correlations here. So the median income is actually the most important factor because it has a strong positive correlation. Higher income areas tend to have more expensive houses. Total rooms, again, more rooms might mean higher prices, but it's not an exactly strong relationship. Age, yes, well. Oh, okay, so this is another way to check for correlation between attributes. And here we are using the panda scatter matrix function, which plots every numerical attribute against every other numerical attribute. So we have like what, 11 numerical attributes. So if we plot each one against each other, we would get like 121 plots, but we don't need that many. We decide to focus on some attributes that might seem correlated with the median housing value. We have the diagonal in which we plot a histogram of each attribute. If I'm not mistaken, what's this? This is the median house value. This is the median income. This is total rooms, and this is the median age of housing, I assume. And if we look at correlation scatter plots, what do we have here? Median house value. And this is the median income. This is the total rooms. This is housing median age. So this is